Hey guys, how's it going? Today as you can see by the title, I'm making the video on what you actually don't understand about the scale of the universe. Just the sheer immensity that a lot of, like, your intuition can't really grasp at the sheer size and space that's in between everything. So I just thought I'd make a video and really want to go over it. So humans about 2 meters tall, right? The tall ones, anyways. If you rounded to the nearest meter, just the sheer size of the Earth to us is just insane. Like, it looks flat. A lot of people are convinced that it is flat, which I think is pretty funny. But it has a diameter of about 8,000 miles, and just to our tiny selves, it just seems absolutely enormous. And in reality, it's just a tiny rock among a normal solar system, among the normal galaxy. And I wanted to walk through the steps of that just to see the sheer insignificance of us cosmically. So our Earth, obviously we have 8 planets in our solar system. Earth is the third, and it's 8,000 miles in diameter, which, if you really think about it, doesn't sound like very many, since it's everywhere you will all spend your whole life on. So then you got Jupiter, which is the largest, and I think that's something like 82,000 miles in diameter, literally 10 times larger. A complete gaseous planet that's just, and it rotates every 10 hours. That's completely ridiculous. But obviously the largest celestial body we have in our solar system is going to be the sun, which is something like 850,000 miles in diameter, I think. It's pretty funny. There's actually logarithmically connected. You have 8,000, 80,000, 800,000 every time there's a step up. I think the sun is 106 times longer than Earth, which is just ridiculous. It's a giant ball of plasma. Now these celestial bodies are absolutely enormous, but I don't think we really understand the amount of space that is actually in between them. I mean, there's 73 million miles between the Earth and the sun. It's just absolutely ridiculous. That's, I mean, like 100 suns. You can fit every single planet in between just the Earth and the moon distance, which is like 238,000 miles. You can fit all the gas giants, all the little, near the sun, terrain planets, rocky planets. You could fit them all right between the moon and the Earth, and it's insane how that's the closest celestial body by far. All the other planets are millions and millions of miles away, but even this close body that we have can fit all the planets that we have in our solar system. So if you keep zooming out, eventually you get to something called the asteroid belt, which many people have heard about, but it's just a belt that's in between Mars and Jupiter that has many different asteroid sizes, and it's actually what we commonly think would really destroy, and that's what any large major asteroid impacts are. They're going to come from the asteroid belt, which Jupiter kind of helps us with that because it kind of pulls them away from us, but we still, are going to get one separate once in a while. Most of the time they aren't going to hit us just because the sheer distance of how far away everything is. There's a lot of space in space. So you have that asteroid belt. I think I looked up one time that it's like the whole asteroid belt. If you took all the mass of all the dust that is collected to make asteroids and the rock, obviously, it's not even half of the mass of the moon. And that's separated over a ring that probably has a diameter of like 250 million miles. And this is literally still smaller than the moon. So that can just put into size how many, like, rocks really, they can't get to too much of a large size. You see the extraordinary ones, but the average size is like, I think 50 to 100 miles. You view something like in Star Wars where you're driving through an asteroid field and you have to dodge things, when in reality, if you're sitting on one asteroid, you wouldn't see another one for hundreds of thousands of miles. It's more like watching out for beached whales when you're driving on the road. It's just, you're just not going to come across it ever. So you got the asteroid belt. Obviously you got each planet. Jupiter after the asteroid belt, and you got Saturn, Uranus, and Neptune. And then after Neptune, something interesting starts. It's called the Kuiper Belt, and it's kind of similar to the asteroid belt, but it's another belt of asteroids but further out, which contain more celestial bodies. Like Pluto is a part of the Kuiper Belt. There's also one called Makemake. Here, I got them listed here. Which, the difference between an asteroid and a dwarf planet, by the way, is it's enough mass that it gets pulled in together to make a perfect sphere. I don't know how they determine, like, if there's a diversification, like how much it can deviate before it's considered a asteroid instead of a dwarf planet, but it's the circular gravity pulling all the stuff together in order to make it a dwarf planet. So the Kuiper Belt is actually 0.05 masses. The the asteroid belt is 0.0005 Earth masses. The Kuiper Belt is 0.05 masses, so it's 100 times more. But you got to think, the Kuiper Belt starts out at the Neptune's orbit. It's so vastly larger that it's going to be even more sparse than the asteroid belt. I mean, not even an Earth-sized mass spread over 800 million. I'm just pulling it out my ass, but just 800 million diameter ring. That's completely sparse. Now, this is the fun part. I think a lot of people know about the Kuiper Belt and the asteroid belt, but next is something called the Oort cloud, which isn't a ring like both of the other ones are, but it's literally a casing of icy bodies that surrounds the whole solar system that we have. And this is the incredible part. It starts at like 30 to 50 astronomical units, which I didn't go over, but an astronomical unit is from the Earth to the Sun, so about 92, 93 million miles. So the Oort cloud starts from 30 to 50 astronomical units, and it goes all the way out to 100,000 astronomical units. So if you think you have the sun, you have all the planets right here, the Oort cloud literally is a thick shell. Like, it's so insanely thicker than all the planets that it's just almost like the nucleus and the electrons outside, just all the icy bodies, which is where most all of the comets that we actually see come from, because there are just so many little ones that the largest one I think is only like 110 miles. It's like weirdly small for how much there is. So we actually estimate that the Oort cloud has like 3 to 5 Earth masses, which is obviously a lot more than the other ones, but you're thinking it's going from 50 to 100,000 astronomical units. That's literally, we almost can't even call that a cloud. I feel like that's you would think that'd be just as barren as regular outer space, but it's the Oort cloud. And if you count that 100,000 astronomical units, that actually continues all the way out to a diameter of 1.5 light years, which is a third of the way to our closest stellar neighbor. And this stellar neighbor is called Alpha Centauri, and it is 4.24 light years away. Oh, Proxima Centauri, sorry. It's a three star system, so I get that confused sometimes. So it's actually Proxima Centauri, and it's 4.24. Proxima is a dwarf star, a red dwarf, and then Alpha Centauri is another system that's really close. Proxima, so Alpha Centauri orbit each other, like really close to each other, like Neptune and the Sun. That's how close they are. And then Proxima orbits around them. Its orbit is like millions of years, but they take only 80 years to orbit each other. And that's our closest system, and we have 3 stars right there, which I think is pretty cool. So the closest star system, 4.24 miles. Then you zoom out all the way to our whole galaxy, 25,000 times longer. It's 100,000 light years. for many, many years, we didn't even think there was more. We thought that was it. It's not until we discovered Andromeda that we thought there were any other stars. I mean, 95%, using your bare eye, pretty much 100% of the light that you see is actually coming from our galaxy. When we see light far, far off, say millions and maybe even billions of light years, you're not seeing a star, you're seeing a galaxy, or eventually a supercluster. So 100,000 light years long, which is just absolutely ridiculous. It takes light 100,000 years. And then actually the rotation of it, one galactic year is actually 250 million Earth years. So it takes us about 250 million to get to the same point from where we begin, which I think is pretty cool. So our galactic neighbor, we have two satellite galaxies that I think are like, they're called like L30, sorry, L31 and L30. It's something like that. It's just a random assortment of letters and numbers, or seemingly random to me. We have those satellite galaxies, but they're really, really small, like 10,000 light years in diameter. They are considered satellites because they're like the moons of our galaxy. But the closest real galaxy we have is called Andromeda. And cool enough, it's actually on a collision course to crash and dance with our galaxy, which I think is pretty fascinating. It's a little bit larger, like I said. Ours 100,000 light years. Andromeda is actually like 170,000 light years. It's a little bit bigger, a little bit more matured, and it's on collision course. I think like 5 billion years it's actually going to dance with us. It's not going to really make any big damage because, like I've said a bunch of times, there's a bunch of space in space. It's just going to, all the stars are going to mix and it's going to be beautiful. Too bad, I mean, that's quite a ways away, but all the stars are going to fit and need right in between each other, and it's just absolutely fascinating. Another one that is a little bit further away, it actually makes a triangle with them, but it's called the Triangulum Galaxy. And these three, plus the satellite galaxies they each have, make up what we call our local group. And our local group takes up a span of 10 million light years. 10 million. Each light year is like 6 trillion miles, by the way, which I'll probably eventually do the scaled up calculations for miles and light years just to see the ridiculous amount of numbers. But 10 million light years for our local group, absolutely incredible. And then this local group is on the outskirts of a galactic neighborhood or supercluster we call the Virgo supercluster. This is 110 million light years long of just thick, dense galaxy-rich space. 110 million miles. It's just... And then eventually they found out the Virgo supercluster is actually just a part of a larger supercluster called the Laniakea supercluster. This is the largest structure of space and star matter that I know of that we are a part of. It is 550 million light years long, which is just ridiculous. The observable universe is 93 billion light years in diameter, and that's not even like light traveled space. That is if we count the stretching of the space-time, which, if this is the largest thing that we're a part of, and it's still not even like 1/200 of the observable universe. It's absolutely incredible. I actually broke down the scales. So if you take I'm going to start with the diameter of the Earth. I know that's a lot bigger than what we do day to day, but that just makes it even crazier. So the Earth is 8,000 miles. The sun is 865,000 miles, 108 times bigger. Cumulatively, still 108, obviously. One astronomical unit is 93 million miles. This is 1,200 times bigger than the Earth. The galaxy, 100,000 light years. 100,000 years for light to travel. This is 7.8 billion times larger than the diameter of Earth. The local group is 10 million light years, and that is 784, it looks like, trillion times larger, which is, you just get into unfathomable numbers. I won't even get to the end till I say that this is just the diameter. Space isn't done in diameters. Space is done in, length. Space is done in volume. So I did some of that too, and we're gonna have to use some scientific notation for this because the numbers are so big. I'll give the numbers anyways, but a lot of people don't know like really high value numbers. So the Earth is 260 billion miles cubed of just rock, iron, molten metal in the center, and that is the size of the Earth. The Sun is 1.3 million times larger volume-wise, and this is still celestial bodies. I mean, if you get into large things like Ton 618, I think the large black hole, like that, the event horizon of that is just absolutely incredible, and that's actually just a single object. That's just ridiculous. And then we get into 1 astronomical unit. That doesn't have a mass, but we'll do the, a sphere with a diameter of 1 astronomical unit. And that is 426 trillion miles cubed, 1.6 trillion times larger than the Earth diameter of Earth. And this is just still comfortably sitting in our solar system. This doesn't even use most of the planets. So let's use the outer Oort cloud. Like I said, it goes from 50 AU to 100,000 astronomical units. We're going to do the outer bounds of it. And if you take a sphere with a diameter of 100,000 astronomical units, you get 420 undecillion miles cubed, or 4.2 times 10 to the 38th power, which is 16 octillion times larger than the diameter of Earth. Just absolutely ridiculous numbers. But wait, we have more. So next you have the galaxy. These numbers are jumping up ridiculously fast. You went from 4.2 times 10 to the 38th to 5.5 times 10 to the 51st power. Absolutely ridiculous. 21 duodecillion times larger than Earth. Then you get the local group, which is 10,000 times larger than the galaxy, which is just ridiculous. And then the galaxy's many times larger than the Earth, and this is completely volume. If you take the local group, the volume of the whole local group compared to the Earth's diameter, which is the only thing you'll likely ever see, it is 400 quadradecillion times larger than the Earth's diameter. 4 times 10 with 47 zeros. Okay. So Laniakea, which is the largest structure that we're a part of, you get the same math scaling up. So let's just go straight to the observable universe, which is a sphere, because the light from outside the sphere doesn't have time to reach us. So we are literally the center of the observable universe, because it has to be a sphere around you because it's in all directions. So the volume of this sphere is 86 duovigintillion miles cubed. That is 8.6 times 10 to the 70th. 70 zeros. I think there are 10 to the 80 particles in the universe. The amount of volume is just ridiculous. And that's cubic miles, not even like cubic meters, like a standard measurement. 70 zeros. And how much larger is that than the Earth's volume? It is 3.3 times 10 to the 59th times larger than Earth's volume, which is all you'll really ever see. 330 octodecillion miles, or times more miles cubed wise. These numbers are just unfathomably large. The largest you'll ever, even to compare to recent events, Elon Musk getting $1 trillion, that's like, say every 100 years it's been a different scale of 1,000. I think like 1810 they got to 1 million. Then 1910, not Andrew Carnegie, but the other one, Rockefeller got to 1 billion, and then 100 years later, Elon Musk eventually got to 1 trillion. You use these numbers, and you ever see the popular, like, 1 million seconds is 13 days, 1 billion's 31 years, then 1 trillion is like 3,000 years? Or no, it'd be 30,000 years. That's just, and these numbers are unbelievably larger than we are ever speaking. And this is partially the reason why I don't think we're alone. I mean, unless there's something literally making us alone. I mean, there's so much space that out of random chance, the law of large numbers would cause something to exist. But I really like talking about space, and that's what part of this channel is going to be about. So I just wanted to ramble on about that. I hope you enjoyed it. Thank you very much.